Hi, good morning. Finally get to doc. Yes, we can see you now nicely.
Uh, Hello, everyone. First of all, we will start the session with Dr. Suresh Mohan. Doctor, do you want to say something?
Oh, this is amazing because I can't believe that a group which we started just for a few friends like me, Kirti, Subhankar, about 10 of us, we just 10 of us, we started for sharing our pictures. And then it turned out that um, um, that we should start at that time when I started, hardly anybody was doing astrophotography, and I started this as a kind of a sharing and teaching and learning and teaching group, and now it's become a group of 4,000 plus people, and we have international famous great photographers, and now we have Anis Abdul come here, and so kind of him to actually explain the workflow of the image process. That's something now that I've completely forgotten and my brain has gone rusted. I jumped into it when he said he's going to uh, do a video kind of an explanation for us. And this is a great opportunity for all of us. I think we should grab it and learn. Thanks, Anis.
Yep. Hi, can you hear me?
Yeah, yeah.
Okay. Yes. Hi, folks. As you can tell, I'm Anis from originally from Madurai, and I started imaging about 4.5 years ago. And from that point onwards, mostly it's been learning from various sources. Either we are, cloudy nights primarily, and then I've had some folks here locally who have come over and have also taught me techniques and software processing as well as imaging itself. So one of the things that we want to do is that everybody has a slice or a view of this big component called astrophotography. And one thing we can do is we can share our knowledge, and everyone is going to be able to basically improve each other. So every time we've been posting images, and then we talk about processing at different levels, but it is really not clear. I don't think it's very clear to everyone in terms of if we can make them improve by understanding just looking at the image, or just putting a little blurb here or there. So one of the things we want to do, or at least I want to do, was to see if I can provide a baseline of how a normal image processing happens via PixInsight. And people who have been using other software tools like Photoshop or Lightroom or AstroArt and stuff like that, they can basically see and compare, and probably also provide additional tips of how we can improve these things. So that's really, and one of the things is that given the fact that we have people at different levels of understanding, I thought today at least we are figuring out how to do this, how to go about doing this thing. So what I was thinking is that I'll just give a very high level basic introduction to PixInsight, right? And we will discuss some of them. I'm pretty sure people have questions. Why PixInsight? What does it really do? That kind of stuff. And then we can go and do a actual image processing via PixInsight. And while doing that, we'll keep monitoring the chat, and we'll try to explain as much as we can. One thing to note is that we will not be able to go really deep in each of the subsystems of PixInsight, mainly because so each of these pixels, areas are pretty big, and usually it will take its own session completely. So rather, we'll give a high-level overview kind of stuff, and then depending on where we want to focus, we can create more sessions in future and go from there. So is it okay for me to go ahead and start, Doctor or Kirti? I can't hear you, but you guys are unmuted. Okay, all right. So the first thing that I wanted to start with is today we are only focusing specifically on deep space image object processing with PixInsight. Okay, we are not going to be looking at planetary imaging. That's a whole different beast, and that will probably require its own sessions and all that stuff. But here we are purely looking at deep space images. And so the question is, before we go into processing, we need to basically set ourselves up for success, right? So as you can tell, there are certain things we can control, certain things we cannot control. For example, we cannot control the weather or whether how bad our light pollution is, what viewing we have, our hardware that we are using, camera, all those kind of stuff. But you can still do certain things before you get to a point of processing, because image acquisition is half the battle and processing is the other half of the battle. So you really want to get yourself to a point where you have the best chance of success, to succeed. So first question is, when you are doing image acquisition, stuff that you cannot control, we can't do anything about it. You are dealing with light pollution, yes. If you have access to dark skies, even better. But few things you want to always do it is, whether you're using a DSLR, a cooled CCD, or a cooled CMOS camera, you must always consider taking flats. Flats are basically your absolute first line of defense against vignetting, FPN, the fixed pattern noise, dust motes. These absolutely need to be get out of the way as cleanly as you can, because in the case of processing, you are trying to get to a very, very faint signal, and anything else in the in your frame is going to prevent it from reaching that point. So this one you can control. You must do it. How do you do it? Right, in DSLR, you simply point to a flat white screen or something, or a uniform source of light, and you basically, without changing anything else, whether how it is connected to the camera, in which angle it is connected, none of those things should change. But you want to shoot it maybe like in the aperture priority mode, to where this histogram is centered, basically. So you're trying to get to a point where the data is in linear range. It doesn't matter what the color is, because for flat subtraction, it's only the intensity that matters. Should not change the focus, nothing. You should not touch anything else. In the case of color, cool CCD, you will want to expose till your histogram is somewhere around the center of your range. For a 16-bit camera, that will be about 30,000 ADUs, because its range is 65,000 ADU, right? 2 power 16. Right, so always consider taking flats. Take at the minimum 20 flats, 20 flat frames. If you are using mono with filters, you need to take one for each. Even if you are shooting narrowband, you should still consider taking it, because in narrowband, a lot of times you can escape without taking flats, but fixed pattern noise cannot be removed without it. So you want to take it. Second is dithering. Dithering is slight motion of the scope between every session, right? Every imaging, light frame, basically. What that allows you to do is that the noise, right, the hot pixels are a property of your camera, right? But they are, and that is going to stay relatively, it's going to be fixed to basically the camera's position. But the actual object that you're imaging will slightly move because of the dithering operation. What you can now do is use this to your advantage. So when you actually do the stacking, you can use a rejection algorithm like Winsor's sigma algorithm or kappa sigma algorithm to get rid of basically the hot pixel, this noise, the satellite trails, everything. Because if you think about it, you are basically saying that I am going to align everything to the deep space object. That means if the deep space object is aligned and the stars are aligned, anything else that is not aligned must be noise that I can get rid of. So basically that's what it does. So we will, we are not going to go into stacking today, but you want to dither your data, absolutely. Especially for DSLR, you need to do it, because you are going to see those horrible slanted red and blue noise that you cannot get rid of, and it's thermal noise, and there's no way around it. So dither every frame if you can, right? So it looks like there's a question, but ideally if a focus is unless they are parfocal. Yes, so see, it does, again, in your case, remember that you're looking for dust mode. So everything else is going to be out of focus, and if you're going to use red channel, shoot with red channel. Take the flash with red channel. You will not be touching the focus. You shouldn't be touching the focus at all. whatever it, take it. Normally, what I do is I usually take flats after every session. But if you can take it before the session, it's totally fine. Some cases, if you're never going to, if you're going to keep the system untouched for few days, you could probably get by with just one set of flats. Completely up to you on how your system is, but you do want to take flats. Do not skip it. That's the thing. You do not want to skip it. Don't try to bring it in and then move the camera. None of this is going to work. You need to take it. And especially given that it's so hard for us to already image, why waste our more energy on that? And let's see.
Or do you use some other light source or some flash?
So few things you can do. Absolute simple you can do is take a white T-shirt, stretch it on your OTS dew shield, stretch it basically, and start shooting. For DSLR, it's straightforward. Just put it on, point to the sky, and just shoot away with your in the A mode. In the case of CCD and CMOS, you have to figure out what exposure gives you the the histogram to the center, basically the linear range. And if the light is fading in the evening time, you'll have to take it pretty quickly. Otherwise, take an iPad and put it in front of that stretched T-shirt, and you can shoot it also. All those will work. So in certain conditions, like if you have high frequency screens, like LCD screen, sometimes if you have those LCD screens and if it is too bright, what will happen is that your exposure speed will be pretty close to the refresh speed, and then you will have issues with flats, but you can always reduce it by adding more layers of T-shirt. So how do you take the flats, right? So take the flat, as I said, you want to shoot whatever be your camera, right? In the case of, as I said, DSLR, you have to put it in the aperture priority mode, and if you shoot, it is going to give you center histogram. Basically, it's going to expose it to the center. That's it. So DSLR is very simple. Aim, do not touch anything. Do not change the focus. Put a T-shirt, on a rubber band. Put it in front of the sky, into your what do you call that? Lens. Point to the sky. A mode. Shoot. 20 of them. Done. Right. In the case of CCD is where you have to think a little bit more. You might want to have a flat, iPad or some kind of flat box. I made my own little flat box. Simply just take little box with LED lights and a diffuser in front, and I just mount it on my telescope. I can post some images about how to build a flat box, but that's pretty simple actually. Does it make sense?
Yeah, thank you. Sorry, somebody replied that he can't hear me, so I just typed the question there.
Okay. Yeah. I mean, the LED lights is very simple to do it, and we can definitely share. And there are lots of options available. It's pretty straightforward. But yeah, we will definitely do that. Dithering, absolutely do it. Do not skip it. Right? If you don't know what dither is, if you're auto guiding, PhD will allow you to dither it. Most of the image processing tools will allow you to dither it. Backward UOS, if that's what you're using to cover, it will dither it. But you should dither it. That's as simple as that. You cannot skip it, right? Once you dither it, you already are having a pretty good, flats and dither will help a lot to get your frame to a point where you can start working on it. But if you start with a really bad condition, it's really hard to squeeze anything out of it. So dark and bias. So here's the question, right? Dark and bias. Bias is very important. You need to shoot bias. Bias is basically trying to tell if there is no light in the system, what is the camera electronics' contribution to signal in the system. So if you completely put in a dark box with no light and you just execute the camera electronics, there is inherent noise in all the electronics there. And what is that noise? Which is typically a fixed pattern noise. And that's what the bias is trying to capture. So what you want to do is you basically want to shoot like 100 frames with the lowest time that you can get, which is the highest shutter speed you can have in your DSLR. Or in the case of CCD, whatever is your lowest possible value. Most of them can go all the way to 0.001 second if it is a electronic shutter. If it is a physical shutter, then you have less. But you want to take the bias, right? Bias is very useful. Darks, on the other hand, can hurt you or help you depending on how you are doing it. Dark is basically talking about the dark current, which is typically related to the temperature, thermal sources in your circuitry that is contributing to basically signal. It looks like signal to you, but in reality, it is originating from the camera. And it is typically linear in the case of CCDs. That's why you can predict, like, let's say I have taken a dark signal, 30-minute dark signal, and if I'm using it to calibrate a 5-minute frame, I can scale it down. The software can scale it down. But if you are shooting dark current at an absolutely different temperature, right? Let's say you're shooting at 20 degrees, and in the morning time you're taking dark current at 40 degrees. Well, it's completely going to be off. You do not want to use it. So in the case of DSLR, anything non-cool, do not use darks. In the case of CMOS, in the case of CCD, you can use darks, but the new CMOS cameras have such low dark current that you probably can escape without it, right? CCDs like Kodak or TrueSense 8300 chips or 16200 chips, you should take darks. There's no reason not to, right? So take bias, take dark if and only if you are having a cool camera. Otherwise, depend just on bias, dithering, and flats to get to your next step, which is what we are gonna do. So once you have this, clean calibrated image, then you can stack them, and now you are gonna be in business to get to the next step, which is what we're going to discuss today, right? Processing. Any questions? Anything you want to generally discuss? Anything? Okay. All right. So let's go to pixel sight, right? So we keep hearing pixel sight. Like, what is it really, and why do you want to use it? Well, so there are a lot of image processing applications, right? You have Photoshop, you have Lightroom, you have Astroart, you have tons of these applications. But why is pixel sight so important, and why do you want to use it, right? And one of the things I've noticed is that people don't think that you're ready to pay a lot of money for the telescope and for this mount and all that, but we really shortchange the software. Pixel sight is specifically designed for astrophotography. It's from the ground up. It's nothing else. There's no other objective for the thing. Everything is targeted towards astrophotography. And it does provide a toolkit that is pretty much unparalleled with its abilities compared to other applications. So what it does is that you do want to use pixel sight as well as you can, plus other applications, right? I typically use it for calibration, stacking, primary processing, and then I finish it in Photoshop. Yes, Harsha is telling, yes, we should take bias in uncooled DSLR as well, yes. Because bias should still be taken at the same temperature, but it is still trying to, since you're going at the absolute lowest speed, absolute lowest shutter speed, the temperature isn't an issue there. Rather, you're looking for fixed pattern noise. So yes, you should take bias as well for uncooled DSLR also, yeah. Okay, so coming back to pixel sight. So pixel sight basically is one of the tool in your, but it's a very powerful tool in your toolkit. That's one thing, right? It does have very high learning curve because the UI is very weird. The way they have implemented the UI is quite weird initially. So it does throw people off. And they have almost nothing in terms of documentation other than tons and tons of forums and presentations and workshops. Very recently, one book came, and that book is not even enough to cover it. I mean, there was one person, I guess Keller or somebody, I think, Warren Keller, I believe. He came with a book now, but it changes so much that you really have to keep using it to get up to speed on that one. There's no way around it, and we need to just do it. There's no way around it, right? So, for example, some of the things it provides are dynamic background extraction. What this does is, in a very dark sky, right? You don't have to deal with background gradients and stuff. But we are all shooting in badly light polluted locations. So DBE is a very strong tool there. Color calibration, same thing. We are dealing with so much noise, light pollution that you need to provide, perform color calibration. It provides, color calibration tools, including photometric color calibration, where depending on the object you're imaging, it actually can tell what the color should be. The temperature of the stars using data collected by other telescopes. So photometric color calibration they've added. Image inspection is very good. Basically, they provide real fast ways to, let's say you are having 200 or 300 images frames. How do you know which are good, which are not good, right? So you want to be able to blink through them. So it provides blinking mechanism. It provides subframe selector scripts where you can calculate the stars shapes, the FWHM values, lots of stuff you can do. In fact, there are a lot of scripts available that can grade your frames and throw away the bad frames, stuff like that. Excuse me. Yes, yeah, you cannot share Pix Insight. No, they won't. Unfortunately, there's no way around it, and and it is an expensive program. Yeah, but yeah. Okay, and then deconvolution is again very useful, very strong, helps a lot in recovering some of the data that got, I guess, convolved. Basically, it's your signal that is basically it's a little spread out, right? You're trying to recover the signal back. So deconvolution is helpful. Mask generation tools. This provides some of the best mask generation tools I've seen. Star mask generations, range mask generations, all sorts of stuff you can do. Pixel math. That's again extremely powerful. You can, do lots of activity, a lot of special, I guess, operations just using pixel math. Mixing, deleting, grading, all sorts of mixes you can do in pixel math. Linear fitting. Also, they have a lot of, and I'll show some of those tools there. So a lot of these tools are just simply not there. Some of them are mimicked, I guess, using plugins, this and that, but purely in this mode, they're just not there. So the way I would want to do it is, you want to use some of these best tools of this product, and then use something else of another product like image denoise or noise ninja. Also you want to mix and match. Basically, your data tells how you want to process it, but this is an essential one to have it. It is a platform agnostic. They support Linux, I guess, Ubuntu, FreeBSD. They support OS X. I know Windows, of course, they do. They are fully multi cores. They support all that. They don't support GPU though. I mean, I don't believe they've added support for using GPUs to speed things up. They said that that's not their priority. I don't know why. They just don't have time for that, I guess. And the more important thing is it's extensible. They have defined their APIs for other people to develop either newer plugins, as well as they support full JavaScript runtime in there, so you can write scripts. And a lot of people do write scripts. I know a bunch of them provide scripts for special conditions, like things like star matching, things like mask, what do you call that, mosaic generation, stuff like that. They've done a bunch of those things. So it's very useful to extend it. Any questions? I guess nothing new. Okay. So the way we want to do is that one of the unique things that I guess PixInsight does is that it supports processing in linear data state. So normally, if you'll notice, when you stack on Deep Sky Stacker, you'll notice that it looks black basically, right? The data looks black until you go and stretch it using your levels or whatnot. So in that state, PixInsight performs a lot of operations in that state. So it's quite, some of these tools work very well when the data has not yet been manipulated right after stacking. Whether it is extracting the background, whether it is color calibration, deconvolution, some of the noise reductions, all those things it provides in linear state. And then they also provide different ways to stretch the data as well, a bunch of them. So you usually want to do all these things in linear state. Once you push it out of linear state, at that point you have the choice. You can export the data as a TIFF format into Photoshop, and you can continue processing there, and some people do. Or you can do processing right here using HDR multi-transform. A lot of times you'll notice that, oh, my core is very bright, like, Orion Nebula core, or some of the galaxy cores are very bright. Well, you'll use HDR multi-transform for that. Local histogram application, so local histogram equalization to basically brighten up some of these fine structures, morphological transformation to reduce your stars, curves transformation, all sorts of stuff is available. That's just very small piece. Okay, so Anis, can you explain more on linear and non-linear state? Okay, so I'll show it right in the actual application itself. But when you're shooting your data, your signal is so less that you'll notice that all your data is really bunched up in your histogram as a very high peak, right? I mean, you're basically your entire data is bunched up as a very sharp peak, and there's really nothing. If you just normally load it in Photoshop, you will see it as a black image, right? So that data is in linear state where it simply is the data that was recorded. That's it, nothing else. And then what you do is you now start stretching it. Meaning you are now basically changing, you're splitting that, for example, I guess we should put a little bit example, but histogram simply says that what is a pixel, what is the value of, I guess maybe it's not a good way to explain. Maybe we can put a separate image for that later, but I guess the way you want to think of it is, you're looking the data that comes out of your camera to be extremely dark and black. And that is a linear state, untouched. Non-linear, meaning linear means whatever data you got, everything got basically the same weighting, right? It's just linear at the point. Non-linear is now just for us to see, we are stretching certain areas more, certain areas less. We want to keep the background dark, but we want to make the DSO brighter. So we are basically applying a non-linear transformation, a function to the data that originally had just the same weightage, right? So we want the DSO to be visible more. We don't want your background to be not visible. Basically you are now applying certain amount of weightage, and that's what makes it non-linear at the point. So that's basically I guess I would say. So in general terms, you shoot something, you load it up, like, a common example is that when you open it in Photoshop, you'll see black, you have to use levels to, stretch it out. That's when it becomes nonlinear. Does it make sense at all? Okay.
Essentially, we are changing the black point, gray point, and white point in such a way
Yep.
that black image looks better with, and then we have this dynamic range compression. Right?
Correct. Right. So you are defining basically what constitutes your start as a black point. So you can decide to basically you are applying a weight to each of the data that you have collected, right? So and as you said that you are going to try, for example, if you are basically weighting the midpoint more, that means the grays more, to basically make certain things become more prominent than other things, and you are changing the black point to hide certain things that you don't want to see. That kind of stuff basically. So you're applying basically a linear data, you're applying a nonlinear function to stretch it essentially, I guess. And that's once you stretch it, then you are loading it in Photoshop, and then you start working on it. So I thought that I didn't want to just go and start dumping information about some of these functions. Rather, it would be nice, I think, would be to actually see an actual processing itself, right? And remember that the workflow dictates how you want to process it, really. And I'm going to do basic LRGB processing for broadband data. Even for DSLR, I usually will split the data between the L channel and the RGB channel and then process them and recombine them. Narrowband provides a different challenge, and that's for a different day we can play with it. A lot of pixel math playing has to be done in narrowband to get stuff to the way where you want, because in narrowband things are completely arbitrary. You are deciding what you want to show, how you want to show. So your degree of freedom is a lot. At the same time, you're also pretty much stuck, how you want to process your data. So narrowband is a different ball game. So we'll get to that later, right? So another thing is that I'll try to explain as much as I can, but again, I only know so much in PixInsight as well. So I'll try to explain. If I don't know, we'll have to just go and research it, basically, right? All right, so I'm going to try and share my PixInsight screen application window, and is it visible now?
Yeah.
My screen? Or looks like I'm being seen rather than the PixInsight window. Oh, it's coming. Okay. All right. Excellent. So here I have, let's see. So the data for this today is an OSC data. No, it is, hey Kuldeep, this is, can you guys hear me? It says, waiting for people to join this video call. Hello? Okay. I lost Kirti and the dog for a second there. So hey Kuldeep, this is not OSC data, this is mono data that I shot here, and I already stacked it, and it is already clean data. Okay. But you can see the PixInsight screen though, right? I guess you guys can see. Okay. All right. So you can see that everything is black here, right? So this is the linear state that I'm talking about. So in the PixInsight, you'll notice that it's basically a bunch of windows that I have here, and I have something called a screen transfer function, pixel math screen. I have a bunch of these things. Okay, this is how it is, and you can see that it is not your usual application, right? You can see that the total functionalities they have is like tons of these things, like address, Hdr Transform, adaptive stretch, background neutralization, channel extraction, color calibration, blah blah blah. All sorts of stuff is there, and none of these actually make any sense if you start working on it. You cannot really be, figuring things out here. It's really bad. I mean, there's really not much in terms of documentation. That's its biggest problem. It has very steep learning curve because of that. It just makes no sense at all. And the UI also is pretty weird also. So it is what it is, I guess. But you can see that I have L, R, G, and B. These I've stacked already, right? I've cropped them, and they're aligned perfectly, okay? So that's what right now we are having it. And this is the linear data, and I'm going to show you by looking at the histogram. And the histogram, if I select L as this one, and you can see that the histogram is all the way bunched to the left, right? Let me see the screen share to catch up. It should show you now. Is it showing my, I guess it's not yet showing my histogram. Because I'm watching the YouTube to make sure that it's catching up. But do you see my histogram window at all?
No, I don't see the histogram window.
I wonder why. It's like almost like it's frozen, or maybe,
I can see
because I can only see like 4 screens there. Maybe it'll slowly catch up. I'll wait, I guess. Man.
I can see your cursor moving at least. But
you can see it, is it? Like, because I can see only my 4 windows there, but I don't see the screen transfer function or any of those things there.
Yeah.
How about I share the whole screen, right?
Yeah.
So let me see if I can share the whole screen. Maybe that'll help. Okay, I'm trying to share the whole screen now.
Yeah, I can see the screen transfer window now.
You can? Okay. So it's showing up right here, right?
Yeah, on the left bottom.
Okay. All right. Okay. So now if I open the histogram transfer function, you can see that still not loading. I don't see it.
No, I think your YouTube may be slower because I mean.
Okay, you can see it, right? Okay. Okay. All right. So here on the left side, you can see that the data. This is the data. This entire frame's data from 0 to 65K, 16-bit converted data. You can see all your data is like bunched all the way to the left, right? And basically, this entire frame's data from 0 to 65K, 16-bit converted data. You can see all your data is like. Looks like Doc is online now. Hello. Okay. All right. So it's basically on the left, right? Now, if you look at it, how do I tell what the data is here? So there is something called screen transfer function. What it does is it only applies some operation just to the screen, but doesn't alter the data. It's very useful to see what is in the data. So for example, I can select this, and if I do something like this, it basically stretches and shows me what is in this particular frame, right? And you can see that this is having M45, right? It's Pleiades. And you can see also the information here. Same thing for R. I'm just trying to see what is in there. Well, that is the R channel and the G channel and the B channel. And you can see that this is the data that is available in there. But the data is not yet changed. The data is still the same. Okay. So if I go back, the data has not yet been changed, right? So the first thing that I normally like to do is basically get the L ready. Basically, all your data, all your strength, all your information is going to come through the L channel, right? Is something wrong here? Okay. All the information is in the L channel. RGB is only going to give us data for color data only. We are not going to use it for anything else. Okay, so what I'm going to do now is I'm going to convert this RGB into a single RGB frame. Is something going on, Kirti, or you guys can hear me?
Yeah, we can hear you. I think the volume for some time went drastically down. I think that's because when doctor joined at that time, something happened. But now I muted us, and then I think it is fine. Guys,
Okay.
confirm if you can hear us properly. I'll just mute myself now again.
Okay. Okay. Yeah, we can post. So here's what I'm just going to show you: a simple pixel math, right? RGB screen frames are there. I'm simply going to just map them basically. I'm just simply going to assign R to the R channel, G to the G channel, B to the B channel. And you can do the same thing in Photoshop, but only after stretching. But here you are doing it while it is still in linear form. So I'm going to simply add it. And I'm getting a frame here. So Control A, you can see that I got an RGB. I'm going to close this. I've already created RGB frame right here. So I'm having an L and I'm having an A. But as you can tell, the colors are completely off, right? I mean, it's like having some weird background, weird everything. So what do we normally do? The first thing you do is to calibrate it. I want to color calibrate it. There are a few things you can do. The first one is normally using what we call as a dynamic background extraction. That can do the job. So I'm going to take a copy of this. I drag it out. I get a clone of it, basically. I can do something called automatic background extraction. And whatever is the default, I'll leave it as is. I'll subtract it. And I'm going to just drag and drop to it. And it is going to figure out what is dominant. It's going to cut out. And it's going to figure out what the background is. And it gives some kind of weird, you can see that some weirdness is here, but it tried to do something. Nothing great, doesn't look good, right? Other option is to perform background calibration by telling the software which is your background, which is your foreground. And that can also be done using color calibration. But another tool is what is called as a photometric color calibration, right? The photometric color calibration, what it does is knowing this target, right? I know it's M45, and I know the colors of the stars in this area. I'm going to go ahead and figure out the stars in this frame, and I'm going to assign colors properly to them. So the photometric color calibration, and I'm selecting a white reference. You need to tell what the white reference is. In this example, I'm just selecting a G2V star. I mean, and it depends. Apparently, there are lots of these different. I see, Doc. All right, so ready to start again. All right, folks. So where we were was we just created an RGB frame from 3 separate channels, right? And basically created the RGB frame. And as you can tell, the color is not right. It looks greenish, and there are multiple ways to play with it. But what I do want to show is some of, again, the objective here is to showcase few of the tools. It's not going to be a rigorous selection of tools, but rather just to give you a flavor of what PixelSet can do. So I'm going to go with the photometric color calibration. You can see in the color calibration, there is assisted color calibration, background neutralization, there is normal color calibration, there's linear fitting, there's photometric color calibration. Let's do photometric color calibration. And what this thing tries to do is, as I said, it is going to go and basically match the stars that you have in your frame with whatever was collected by the surveys, I guess, in the database. And it's going to match the color, and it's going to basically try to assign the correct color to the star, which in turn will push the relative colors of everything else in the frame. So if you select the right white reference, it should theoretically come correctly. But it is not always accurate, but it can be quite accurate if done correctly. So in this case, I've put the image parameters. This is the M45's parameters. If you look like a search coordinate, you'll notice that M45, I've pulled it up from Simbad, and it is, RA is 3 hours 47, and declination is 24/7. So, and then the focal length of the scope, this was with the Takahashi FSQ 106ED, which with a reducer, it's a 350 millimeter focal length, and the pixel size was 3.75 microns. And you can notice that they are not giving any documentation, nothing. You can notice that they don't even tell what this is. They just expect you to know. But you can see if you mouse over, it'll give some little bit of information, like approximate focal length in millimeter. Basically, this is for plate solving. It wants to solve the object that you have on the screen. It wants to know what it is, and then it will attach it. So if I do that, let me take a copy of it. To take a copy of it in PixelSet, you just drag this and drop it. It creates a new copy. The reason why I'm doing is I want to see the difference between the two. So let's do this for this RGB. I'm going to drag this, and you can see this little triangle at the bottom. I drag and drop. That means, apparently, it's supposed to mean that it is, executing that particular process on this particular frame. We have multiple frames, so we drag and drop down this specific frame, this RGB frame. And you can notice on the left, it is trying to do a bunch of things. It is figuring out the stars. It is figuring out all sorts of stuff. It's doing multi-scale medium transform, all sorts of stuff it does, transforms to figure out stars only. It wants to extract the stars, and using the star position, it wants to figure out where in sky we're looking at. And you can notice that it has done a bunch of things. It shows the star detected values and the color difference values. It's basically created a new curve based on what we have to what should be. And if you look at it, the color has changed, and you can see it's become blue, the backgrounds have become black, right? So the photometric color calibration can work really, really well if done properly, and that first of all gave you the color reference for you, right? Now let's close this guy, right? And let's keep this RGB in one side. Let me just keep it here. Now, our main objective here is to perform all our operation on L. But there was a question. What if I start with LRGB image, right? What if I start with a DSLR image? How do I do it? Well, let's just take this as an example. This is an RGB image. And here in the top, you'll notice there's a little word that says gray. So gray means it's a single channel image. If it says RGB, that's a multi-channel image. So select the RGB, and there is a process called channel extraction. The channel extraction, what it does, allows you to extract specific channels. And I want to pick out the luminance only. I want to work only on luminance. How do I do that? I can change the color space from RGB to the CIE LAV mode, right? And I'm caring about only the luminance channel. I don't want the A and B channel. If I drag and drop that, the same technique, drag and drop, it is going to create a luminance channel. You can see that this guy is provided as usual. This is a linear data, so the data is not stretched. And you can, if you control A, I mean, if I stretch it, you will notice that it is the luminance data of this guy. So what you would do if you're starting with color data, well, you want to use channel extraction, extract out the L, and then process everything. Put all your processing in the L. Do not do it on the G, because when you're processing on a single channel, you have far more control on what you want to keep, what you want to hide, what you want to get rid of, what you want to enhance. And that is a very powerful tool. Think about that, right? If you are doing it in multiple channels, I want to push the saturation of yellow stars only. It might end up pushing saturations of other things and making garish, overcooked colors in other channels. You don't want that, right? So you want to pull and focus on specific areas. That's the reason why this mono processing is very, very useful. So that's the reason why we call LRGB, because you're processing L and then you're processing RGB, and then you finally are going to combine it, right? And I'm going to go overboard here, try to make it more garish than what it has to be just to prove a point, right? So I'm going to close this up. We don't need this. So I have this RGB ready. I'll keep it, right? It's unstretched data, but I'm going to keep it here. I want to focus on the L data, and this is the L data that I want to play with. As we know, this is still a linear data. So I need to create a mask. The basic mask I want to create is called a light mask, meaning we want to protect the high signal area, and we want to allow noise reduction to happen in low signal area, for example. What is the easiest way to do it is you just take a copy of your actual data, the DSO itself, you create a copy, but this is still a linear data copy. So if I, for example, if I close it, it doesn't do anything. So what you do is we can apply what we call as a histogram stretch, which is basically converting this to a non-linear data. We are basically going to make this stretch permanent. So the way I'm going to do it is I'm going to take the screen transfer function, which is basically tries to show all the data in the frame, whether it's good or bad, doesn't matter. It shows everything. So I'm going to drag and drop on the bottom bar of the histogram. If I drop it, you will notice. Okay, let me. There's also this O is called preview. So I'm going to show a real-time preview. So I'm going to drag and drop on it, and you'll notice that this thing blew out completely. No problem. Reset it. It's back here. And now I'm going to apply the data. So once I apply the data, this data is now ready to. Oh shoot! I didn't apply. Instead, did I apply here? Okay. So I'm going to apply this data here. So I'm going to select L clone. O. Control A. Drag and drop. Okay. So this is my light mask. So I'm going to rename this guy to light mask, right? This is going to be a mask. You know why is it a mask? Because let's say I'm going to select, and I'm going to, if you have to mask an image, you have to basically take and drop basically on that image, and it looks like that. And the red areas basically are now masked, and the white area are unmasked. So if I do something here, only the data that is exposed is going to be applied. But if I want to do noise reduction, I need to invert the mask, right? I want to protect the signal areas, and I want to attack the background areas. So to do that, what you'll do is you'll simply go and hit invert mask, Control-Shift-I, or you can use one of these icons and do it. So if I do it, now what you'll notice is that the high signal areas are protected, low signal areas are exposed. So that's how you mask stuff in Pixel. But for now, I'll just remove it. Deconvolution is an important thing. Well, let's see how deconvolution works, right? I want to show that also. Notice these little strands here. These are pretty well focused image, but I still want to, extract more. I want to, let's say, basically pull as much data as I can. So to do that, the first step I want to do is deconvolution. Because of different processes that we have, atmospheric processes and all that stuff, your data is basically getting smeared. It is basically getting convolved, and to its surrounding. And what we want to do is that by measuring a known source, in this case a star, to see how much data should have been, how much the star profile should have been versus what is already there, we can figure out how much data has been spread out, and then you apply that to the entire image to sharpen it up. It's called, to do that, you are doing something called a measurement. You have to do point spread function measurement. Basically, apparently it's all mathematical signal processing stuff, but you are calculating the point spread function. And the point spread function is the first thing you need to do, which is, I'll go to dynamic PSF, which should be right here, right? Wait a minute. Let me see if you can get rid of this guy, get rid of this guy. Where do I have it? Oh, sorry, 1 second. Sorry, I'll close this guy. This is another example I want to show. We'll come to that later, but let me open the dynamic PSF function. As I said, in the dynamic PSF function, I'm trying to tell the system the stars that it should look for and figure out what is the signal that got convolved. So to do that, you simply go and select a bunch of stars. In this case, I'm not going to do a lot. I'm just going to do as an example. I don't want to waste a lot of people's time here. The moment I click on it, it is detecting the stars and it's giving me some values here. It doesn't matter what it is. You just simply do it. You want to select stars all across the frame. Ideally, you want to select like 40 or 50 stars, right? So I keep doing this, keep doing this, keep doing this. Assume that I've taken, and you cannot have any Gaussian stars, meaning Gaussian distribution means that star is saturated, meaning you can't tell the difference now. So normally stars have a specific FWHM style where certain amount of brightness is supposed to be in certain radius, and then beyond that point, there is expected brightness drop off. That is what they are using to figure out the convolution, right? Data. So let me get rid of all these Gaussian stars because those are saturated stars, which we don't want. So I'm going to select a bunch of these stars. They assume that this is hundreds of them. I didn't select. Select all of them, and if you click on this little camera button, it generates what is called as a PSF, point spread function. Keep that ready in one place. Close this guy off. Okay. Second thing I want to do is I want to protect all the areas. I only want to do convolution of signal areas only. I want to basically apply this convolution function for signal areas. Areas that don't have any signal, I do not want to do any kind of deconvolution. So to do that, first I need to provide a star mask. To do a star mask, it's very simple. There's a star mask transform that they provide, and I've already created a bunch of process for it. But it's nothing other than, if you open it, it's a star mask with different parameters, which tries to detect different star sizes. And I simply just drag and drop on this to create. Wait, I'm just basically creating a star mask. Let me run through this and build a star mask. Here is another mask. And as you can tell, Photoshop is not going to have any of these functions. It's just not what it's designed to. So, and we are doing everything in linear state. So let me complete the star mask. It takes more. I mean, it does suck up a lot of CPU though. You do want a beefy system for this one. Okay. So I've created different, basically I'm trying to capture as much stars I have in the system by having different parameters. The tiny stars, slightly bigger stars, very big stars. At the same time, I don't want to capture any DSO. So that's where the whole masking stuff comes. So I'm basically now adding all three of them together to get a pretty accurate star masks. For example, you can see how it looks is if I go and drag and drop my star mask on it, you'll notice that all the stars are basically available now, right? I mean, you can see the stars, everything else is protected, only the stars are unprotected. So it's a good star mask. So let's keep the star masks. Also, here, I'm going to keep this safe. I'm going to use it.
Pixel Mac to add all the masks. How did you add?
Yes, what I do is I simply just create these three different, one single parameter cannot capture all the stars, right? Some of them can focus specifically on the tiny stars. some of them to the mid-level stars, some of them to the last stars. So what I do is I simply create 3 of them, and I just came with the basic idea, right? And then do a max function. This is the main thing, pixel math. They provide a bunch of mathematical operators that you can use, adding, subtracting. You can write scripts here. You can do a pretty complex scripts right here, right? You can do subtraction, if conditions, all sorts of stuff you can do. And again, I'll show you some of them if you want. But basically, this is a simple. I'm simply applying the max function. So if a star is found in one mask and not in the other one, max them so that you basically capture all the masks. So I have the star mask to do that, right? Now the third one I want to protect the background, because I do not want to apply deconvolution to background. I want to apply it only to the foreground, to the DSO. So to do that, what I normally do is this: I basically take the star mask and just use this as a mask itself. So for example, let me make this mask a little bit more harder, basically, I should say. So I go here and I select my light mask, clone, and I'm just simply going to clip it, right? I'm going to just go clip it, clip more. So I'm going to if you notice, I just want these strands to be deconvolved, right? I don't want to do anything to these this surrounding background. I don't want to do anything to that, right? Because that's going to cause bad artifacting, right? So we don't want that. So I'm going to select this guy, and I'm going to put it. I'm going to first put it. I'm going to protect all the background and allow only my my DSO to be available for this operation. And let me hide the mask. The mask is still applied. If you notice, there's still this color is there, right? I'm just hiding it. The mask is still there. It's just not being shown. Okay. Deconvolution is a long-running process. You don't want to do this, and it takes really boring. So what you do is take a small preview, right? Take a little portion like this, right? You want to see what happens when you apply this function and see if you like it. If you like it, then you can apply the whole thing to the full function. So let's look at this guy. I also want to make sure that I don't want to. Let's see how much detail I can get out of this guy. So I want an area with some detail that I want to look at. So you can see there is this area. There is this area. So let's see what happens if I do deconvolution. Deconvolution here, there are 3 kinds of PSFs you can develop, which is called parametric PSF, where you can tell what we are trying to model. The point spread function, you can provide it. You can do motion blur PSF. Assume that you have a very small blur due to your camera moving slowly, left, right. A star should have been only in, like, let's say 8 pixel square pixel. Instead of that, let's say it's like a horizontal line or a slanted line. Then you can use motion blur. You can change this angle like this, right? For example, you can rotate it. If your stars are looking like this, you can say this is my PSF. But we are not going to do that. We are going to say external PSF. The external PSF is, remember the point spread function we created? That's what we're going to use. And I want to protect my stars local support. So you need to provide a star mask for it. And I created a star mask and I named it a star mask. And I gave the name right here, star mask. And this particular function can create this bad side effect called ringing. The stars can have black rings around it. It looks really ugly and really kills your product. So you want to protect it. So you want to do local de-ringing, and you can change this guy. Normally, deconvolution will also cause noisy result. It can cause things like lumpy output. So what you do is you also do a gentle noise reduction as a part of your deconvolution. If you think about, I don't know if you guys have done registacks in planetary. If you do wavelet sharpening, you also want to do a certain amount of noise reduction to smoothen it out. Same way, you can do wavelet regularization to reduce, basically make it smoother, and different levels, basically. I mean, this is again by, experience, I guess. The algorithm you want to use is regularized Richardson-Lucy algorithm. There are Van Kittert or Sittert, whatever. That is also quite commonly used for planetary, but we are not using planetary. We are using regularized Richardson-Lucy. That worked out quite well for me, at least. So I just stick with that. And here is the control that you normally do: global dark and global bright. You never touch the global bright, but you do touch the global dark. I start with 0.005 and move from there. But let's see, because that's what I use as my default. I drag and drop to see the effect of this guy. Yes. So it's doing a bunch of them. And you can see there's a subtle difference, right? Just to see that, let me go back and forth. Can you see what is happening? You can see that the star is tightening up a little bit. This look at this star, or look at this guy, look at this particular star. You can see the star is tightening up. Right? Can you guys notice it? Also, look at this white line here. You can see it's becoming a little sharper, right? You can see that, right? Like that. Is it apparent? Can you guys see it?
I mean, I think it's not apparent.
Let me see it like this. Maybe if I zoom out more, you can see it I'm doing like, right? So the stars are tightening up. If you look at some signal area like this, you can see that this line becomes brighter and all that stuff. And the faint stars are coming out, all that stuff. So remember that I did not do a good job of collecting a lot of stars for PSF. So PSF could be wrong, but this is purely just to show you guys. So I'm gonna do the deconvolution. I assume that I like this result. Assume that, right? Because you can go really bad if you deconvolve too much. You will get this ugly artifacting, and all sorts of ugliness will occur. So you should be very gentle with it. But this is an example of, assume that this looks good, this kind of stuff. So I'm dragging and dropping onto it, and it is performing the whole deconvolution to the entire screen now. So that's the first step. So I always want to do deconvolution first. And to do that, you want to try it over and over again till it comes to a point where you like what you like. Certain times, people want to go over sharpened look. Some people don't want to do it. If you think about it, stars can look with very hard edges, look ugly. They look hard edge stars do not look normal or natural, because stars will have the smooth drop off. They should look like almost like a mild drop off. You don't want hard edge stars, which is usually what happens if you over sharpen things. That will happen here as well. So for example, if you look at it, Control Z, so if I go back and forth, you can see the difference. Let me see if we can zoom it here, right? Look at this line. If I go back, this is very, fainter, this particular line. If I go right like this, you can see it's more prominent, right? Less, more, less, more. Right? Does it make sense? Is it visible? Hopefully, because it is very subtle, but you don't want to overdo it. So,
Yeah,
like this,
it's visible.
right? So now let's assume that this looks really good, and you want it to be very smooth and all that stuff. So back and forth, you're happy. The next step is noise reduction. Okay, tons of tools are available for noise reduction. Pixelset provides some of the best tools, right? One being TGV denoise. There are other noise reduction tools available, ATROS, wavelets. There's also CDNR. Let me see if we can find all those. Noise reduction. If you look at noise reduction, ACDNR, a lot of people love this TGV denoise, MLT, MMT, multi-scale medium transforms, and multi-scale linear transforms. There was also one other interesting tool I forgot. There's one more called, forgot the name already, but there is one more script available also. But anyway, my choice, yeah, go for it.
Mule denoise, right?
Mule denoise, yes. So people love that too, right? I have been sticking with TGV denoise because number one, I don't like denoise. I do not like noise reduction, first of all. If you can tell it's noise reduced, it looks really ugly in general, in my opinion. So you want to keep it to a point where it still looks a little grainy, because it feels it should look as if, again, it's completely up to your taste, right? What you want to do. But it's all up to everybody's taste. But I usually go and do TGV denoise, which is total something variation, total generalized variation, or something like that. Let's see this guy. Okay, this is TGV denoise. And what this guy does is, if I go and take mask and remove the mask, let's look at this as an example. You can see that the background is a little grainy here, and there is side signal areas. If you do denoising using other applications, they can't tell the difference between high signal areas versus background. It doesn't know. Wherein here, these guys mathematically, I guess, apply, using a mask. Again, you need to provide a mask for it. Using a mask, it can detect which is the foreground and which is the background and which one to attack. So it can do a real good job. If you look at this local support, there's a tab called local support right here. And the local support, you need to provide the support image, which is the mask. In this case, again, the light mask, which is nothing other than a stretched version of the image that you're trying to operate on. And normally I just give the light mask. I do not touch anything else. I leave everything in default. And then this edge protection, how much of an edge are you going to protect, like as it comes closer and closer to the actual signal? So this edge protection is what you'll be playing with. Let's say, just to give you an example, let me go overboard with this noise reduction. So again, let's do it on the preview, drag and drop. It's going to run through it. And hopefully this is clear once it completes. And you can see that the noise reductions occurred here, and you can see it's ugly, basically. It really destroyed a lot of background data. Ugly stuff, right? But you can I'm just doing it just to show you. But ideally, what I do is I'll just simply keep it very, very subtle, like, 2 point something. Let's drag and drop here. By the way, no data change has occurred yet. We are only previewing it. So data has not changed. Now I'm reducing the edge protection, basically. I'm gonna, and you can see that it's a little bit more gentle. If I go back and forth here, you can see back and forth. You can see that the background graininess has reduced. Right? Can you? Is it apparent there? Right. So you can see that there's a noise reduction there. That let's say that we are happy with it. Normally, you can do multiple. TGV denoise works very well, but it can result in high frequency artifact in the background. It will look like what they call as an orange peel effect, like how an orange peel looks bumpy. So if you do too much of TGV denoise, you will get a orange peel effect that you want to avoid. Typically, either you reduce the strength of your TGV denoise, or the next step is usually you can do TGV denoise, and you can also do the linear multi-scale medium transform. That's another noise reduction technique. You apply a linear mask on it, and you can control that as well. If I've reached a point where I have to apply TGV denoise and the multi-scale medium transform, I know my data is really poor, basically. At that point, things are not looking good, in my opinion, because every time I've reached a point where I have to do this, I've never really liked my end result. So most of the time, that usually means that you have to go and collect a lot more data. Basically, that's that one. But it's still a tool available to you. Some people prefer multi-scale medium transform. Some people prefer mirror denoise, TGV, linear TGV, MMT, all sorts of stuff. But I usually just do TGV denoise. So let's say that I'm going to do that now. Am I going too fast? Hopefully, it's not meaningless at this point. So what we have done so far is we have basically created a RGB image. We have calibrated the colors, and we have left it alone. We have not done anything to it. We took our light channel, right, L, we took our L, and now we are trying to basically squeeze out as much data out of it as possible, because that is what is going to provide the detail layer. L is what is going to provide the detail layer. And you will soon see that I will destroy the RGB details completely. I do not want any data from or any detail from RGB. I want RGB layer to only contribute the chrominance data to it. No, nothing else. I do not want anything else from RGB, right? That's what I'm going to do. So that means everything that I'm going to do is going to be done at the L layer, right? Makes sense? Hopefully.
Yes.
Okay. So now at this point, I'm ready to stretch this image, right? So the stretching, which is where now I'm going to go from linear domain into non-linear domain. I'm going to start using our favorite tool, which is histogram transformation. So histogram transformation is your stretching. It's equal to your levels in Photoshop. So I'll select L. And what you want to do is there are multiple ways to stretch. Histogram is one of them. There's also, I said, there's an arc string, arc sync sin H stretch that you could also do. I've not done it. I use it only for color data, but you can see that it is also available for stretching as well.
Do you prefer mask stretch or do you prefer histogram?
See, I do not like mask stretch because the stars become super weird with it. And I've tried it, never really liked it. So basically, I do not use mask stretch. I've tried enough of mask stretch. The stars become like really weird with it. And every time I've realized that, us controlling the stretch results in a better data than mask stretch. Mask stretch is nice if we are not able to do a good job with it, but I found at least that the histogram stretch works quite well. It's vanilla version kind of stuff, I guess. So if you look at this, what I do normally is I do a series of 2 or 3 stretches. Sometimes I'll do basic stretch once, and then I will put a mask on it and just stretch the DSO. If let's say my background is really ugly and I have a lot of dust modes, I didn't have a good flat calibration, and flats have, if I didn't do flat calibration, I've left lots of these dust modes and all sorts of weird things. In those cases, I will have to stretch only to a point where it is not visible, and then I have to use masks to just stretch the DSO. Usually that looks ugly, but you can get by with it. For example, here, first stretch. I do a first stretch. I usually never go past the 1/4 mark here. Basically, keep the peak at 1/3 typically. That is the first stretch. Every time you apply a stretch, you reset it. The first stretch is over. Now, what you can do is you can basically clip it. As you can clip the black point, notice how much of data you're clipping. I notice that I'm not clipping any data at all, 0%. So I can really go all the way here, and I push the black point down. Right now, the black becomes really dark. Again, reset it. I can stretch a little bit more now. Bring it back to 1/3 now. Okay. When it comes to 1/3 now, and when I look at the data, and I'm saying, okay, is my background looking good? Is my details looking good? If I'm happy, I'm going to stop at that point. But you'll notice that the more you stretch, the background is starting to fall apart. Your stars are going to become bloatier and all sorts of stuff. So at some point you're going to stop, and I usually stop right at 2 stretch or 3 stretch maximum. Usually one main stretch to 1/3, clip the black point to a point. Maybe I'll lose some amount of data there, but usually I'll never go for more than 0.01% of the shadows, and then stretch a little bit more to bring it back to 1/3, and I'm happy at that point usually. So let's assume that we are happy at this point. Now the question is, okay, what do I do now? I'm in a linear domain. This particular file now can be saved as a 16-bit TIFF, and you can open it in Photoshop, and you can continue processing there as well at this point, because now you've entered into non-linear domain now. Right now, what can I do? I can do a bunch of stuff here. First thing I do, let's pretend that this is a galaxy, right? And in the galaxy, I want to do HDR transform. By the way, guys, hey, it's already half an hour past our targeted time, so I'll try to close it off pretty quickly. I know people are going to be busy, so I'm quickly going to close this off. But let's say that I want to do HDR. I want to basically go for HDR. What I'll do is, if this was a galaxy target, I will do HDR transform at this point. Depending on the target, the number of layers have to be changed. If you're targeting large scale, big large scale structures, you have to change this layers counts basically, and basically I will apply with a lightness mask. Lightness mask meaning, again, I want it to apply it only to the high signal area. Do not want to play around with the background, so keep the background the same. Just do an HDR transform of this high signal area. Look how bright this is. It looks too bright. Let's see what happens when drag and drop to this guy. And you can see that this HDR transform basically converted from this bright oversaturated thing to this. Basically, now we have recovered more data, but again, you want to what do you call that? Control this well, because it can look very flat, it can look unnatural. So usually what you can do is do a combination. What you do is you basically take a copy of it, right? So for example, I have this L and I have a copy of this L clone, and I have two copies of these two things now. So one is with Hdr Transform, the other one is without Hdr Transform. You know what I can do? I can use pixel math at this point to mix them together. Let's say I want a little bit of this, little bit of that. Let's just, as an example, I'm going to say 60% of L plus 0.4 times of L underscore clone, and create me a new image called L1, right? Something just like that, and I hit plus, and it created somewhere in the middle, right? Right now you can see that this guy is not as flat. Let me close this guy. Let me close this guy. It's not as flat as this one, right? But it's also not as saturated as this one. So I am deciding how much mix I want. So again, pixel math gives you that control, right? Let's assume that this is what we're going to use now, just for kicks. You can now do what is called as a where is my friendly local histogram equalization? Local histogram equalization, what it tries to do is, instead of applying histogram to the entire image, it is going to take a very small portion and it is going to change the histogram of that small little squares. What this allows you to do is it boosts the contrast of very, very fine structures. So let's say I want to increase the filaments here. I want to make it very, cool, right? First thing I want to do is I want to protect it first. So I'm going to use a very strong mask, right? I don't want it to apply it on my background. So I have a very strong mask applied. Let me look at the preview and look at the histogram. Again, knowing this image, I know I wanted, these structures are very fine structure. So I want to go very small, like 24 or 16, something like that, pixels basically. And the amount is going to be too much. 1 is too much. So I'm going to go 0.1 or 0.2, something like that. Histogram resolution, I want as much resolution as I can. And contrast, I want to increase the contrast. I want these filaments to pop out, right? So let's say that I'm going to try out with a 0.15 amount. I'm going to drag and drop and see what the effect of this local histogram transformation is. And something happened. Let's see what happened. Well, you can see if I go back and forth, you can see that the contrast has improved, right? The black portions have become a little bit darker, right? You can see this. So the HDR transformation usually reduces contrast. You can recover a bit of the contrast using local histogram equalization as long as you mask it very well and apply it only to the areas that you want it to, because local histogram equalization can increase noise in your system. It can make it noisier. So you want to apply it to very high signal areas only, and that too you want to control it very well. Again, there are a lot of ways to skin this one, but this is one of the ways, because you can make multiple variations of this and still use pixel math to add it together too. But we are not going to do that right now. Just for the example, I'm going to apply local histogram equalization to this stretched HDR image, right? So I'm going to apply it, and this is again a pretty heavy duty function. It takes a long time, but it will complete. Almost over. Okay, so now assume that now we have reached this point where we are happy with these details of strands. We have liked this gas, whatever has come. Let's say we're happy. Now I'm ready at a point that I think my L is ready to go. I'm happy with the L now. Okay, so I'm gonna go ahead and get ready for my RGB. So it's time to play with RGB now. So let's say that I'm happy with this RGB, and I'm going to start stretching it. I'm not even going to do anything to it yet. Normally, what you want to do is you want to do noise reduction right here, because we don't care about any of these details. We don't care about these details, nothing. That's why if you notice in LRGB imaging, right? In LRGB imaging, you are shooting a lot of L and very little RGB, because you're only going to use just the color information. You don't care about any signal from the RGB. Hey, Kuldeep, so 12-bit CMOS is exactly the same. What happens is that once you load it up here after transforming, after you stack and everything, the only difference is that for 12-bit images, your dynamic range is lower because you have much lower resolution. But the more you stack, the more you're going to recover the dynamic range. So once you want to get as many number of frames as possible to recover the dynamic range for the 12-bit CMOS. Once you are done with it, you bring it in here. It can now be treated as a 16-bit image. No difference at all. So there is no change, okay, from a 12-bit source at all. It doesn't matter. At this point, everything is considered now we are looking at as a 16-bit image. Basically, 0 to 65K, I guess. Anyway, this is RGB. Assume that I'm going to do a strong noise reduction. Again, in our example, let's just assume that this is a noise-reduced image. Maybe I can do it. Let's go ahead and go crazy with this thing. I'm just not even going to care what I'm going to, what happened here? Light mask. Light mask. Oh, come on. Sorry, guys. Give me 1 second. AP data. Sorry, probably I should have aligned both of them together. Let me align this quickly. So this is L2. So I'm gonna convert. Give me 1 second. Image. What I'm trying to do is that what it's telling me is that the RGB image is not having the same geometry or same shape or size as the L image, and basically you can't use it together. So what I need to do is I need to align it together. So I'm simply gonna align my RGB to my light L. L. So I'm just gonna drag and drop onto this guy, and it's gonna align it. Oh, come on, yeah. Okay, so this is my aligned RGB, so I'm not going to care about this one. So this guy is what I'm going to be using now. So, okay, this is my registered RGB. I don't care about L2 at this point. So now let's do denoise for this now. So I'm going to drag and drop my handy dandy TGV denoise. It'll take longer mainly because it's a 3-channel denoise now, because RGB, it's going to do that. So let's wait for it to complete. We're almost at the end of this thing, at least at the basic point where we will get an LRGB output. And once you get an LRGB output, at that point, again, you are going to go play with noise reduction, star reduction, color manipulation, whatnot, whatever you want to do at that point, you'll do. At that point, you could probably export it to, Photoshop and use your other plugins if you want. There are real nice plugins available in Photoshop that you can use, like Annie's Astro Actions, the Nick plugin. All these things can help. There was another Noise Ninja. Also, all those things can work as well. You could even push it to Lightroom and play with there as well. Sometimes that helps a lot. But at that point, you are basically ready to go. As you can tell, it has completed noise reduction on channel 0, which is R, and has done it on channel 1, G, and now it's going to complete it in B. But you'll notice that I don't really care about it. The only thing I want to make sure here is that the colors look correct, which means, the central 2 stars are very interesting to look at. This particular pair, you will see the top one is a yellow pair, the bottom one is a blue one, and in these 4 stars, you can see that there is blue, yellow, blue, yellow, yellow. So you want to make sure that these things look correct, because at this point you want it to be correct. Let's do this. Okay. So the noise reduction is completed. As you can tell, if I go back, there is noise here. This stuff. Right click, the noise is gone, reduced at least. And I'm going to do a stretch now. So I'm going to stretch this guy using histogram transformation. Select RGB, There is a bunch of ways to do this. Again, I'm gonna mix it with L. So I'm gonna do a very basic stretch. I'm gonna do a small amount of stretch. This is good enough, really. I really want to keep this one dark because when I mix it with L, I tell how much of L component has to come in. So I'm going to do a very little stretch, just enough for the colors to be available. That's it. I don't want any more than this, and I'm good, right? So this is your RGB ready to go. Well, it doesn't look impressive yet, right? It looks pretty anemic, but our L is basically ready to go. We have fully, prepared L ready to go. So let's see how we want to do this. And clearly, these two guys are completely different. One looks with lots of data, one looks very little data. What do we do? First thing, we want to destroy all these details in L. And to do that, the best tools for that is Atros wavelets. So in the Atros wavelets, it basically breaks this, signal into different frequencies, right? So it breaks it up into, very small structure, larger structure, like that. What we do is simply select each of the layers and we remove the detail out of it. So we uncheck the detail, basically. So it's basically we're saying that we don't want any of the detail in layer 0, layer 1, layer 2, layer 3 and 4. And layer 1 is fine detail. Layer 2, you can say the scale is 2. Layer 3, the scale is 4. Layer 4, the scale is 8. You can increase the number of layers to 5, and I don't want layer there also. Let's say that I'm going to get rid of all the data here. And if I drag and drop, what's going to happen? It's going to basically make it blurred. You can see this is all completely blurred, right? So you can see that like that. Let me make it 4. So you can see that this guy is all blurred now. Going to be blurred again. So you can see that the structure is sort of there because I only took out 1, 2, 3, 4. If I did 5, even more data will be removed, but it's all there. Okay. Now let's get ready to mix it. So I'm going to take 2 copies of it just to see the difference. I have copy 1 and copy 2. Here is my L1, which is my mixed data of L, and here is the original L, which has no HDR and nothing like that, just to see the difference. So here is my high resolution thing, and here is the original one. All right, so let's go to LRGB combination. In the LRGB combination, I'm going to mix L to my data here. So when you're adding this, you need to tell, let's say the L is, we're going to do the first one now, L, okay? Here is the lightness and saturation. This is the transfer function, meaning if I increase this number, the result is going to be brighter. Okay, if I reduce this, it's going to be darker. In the saturation, if I reduce it, it's going to be more saturated. If I increase it, it's going to be less saturated. So let's say I want to start with 0.3. I want to make it a little bit more saturated, because what's going to happen is that when it starts to mix the L channel to the RGB, colors are going to start diluting it. And what we're going to do is we're going to boost the color. And one more thing is that if your RGB is very noisy, like DSLR data, remember we were talking about DSLR, you start with an one-shot color, and then you're splitting it using channel extraction into L and RGB components. Your RGB will still be noisy. So chrominance data, noise reduction can be enabled. Hey, Harsha, so the reason why we are doing it is we want only chrominance data from the RGB. We do not want it to contribute to any kind of structure detail, final result. We want the structure detail to come from the L channel only. So we blur it out so that it doesn't provide anything else except just the color data. The LRGB combination deals with how it is going to mix it properly, and you will see why also. So here's the L, which is this guy, and I'm going to drag and drop on the bottom one, and let's see what happens. And you can see that it has done something. It looks bright, it looks great, and it has done some mixing here, right? So what you can do is you can reduce it even further, or you don't want it, you can reduce it more. You can increase the lightness. Let's go back and try it one more time. And here you will be playing with it. You will make it darker, you'll make it brighter. It's completely up to you. Now, let's say that I'm happy with this. So you can see that the original RGB, just as an example, let's do this. Let's go here. Let's see how the original RGB looked like. The original RGB looked like this. It looked like this, right? Now the mixed RGB looks like this with color data, yellow stars, blue stars, whatnot, and the detail, the dust detail from here. So basically we took this guy and we mixed this with it. Now let's see about the second one image. And that one is, I'm named it as L1. I'm going to put L1 here. And I am going to mix it a little bit. Let's see. This guy. It's the second image. Just want to see variations. So no need to do linear fit. No, you don't want to do linear fit between the two. No. You can do it, but there's almost no reason for it, really, because you are going to be playing with it. You're going to mix. You are going to be changing it around. Believe me, it really hasn't worked well. Normally, you can try to do linear fitting. It works, but as you can tell here, these are the two versions we got out of this whole thing, which is, the more grainier, not the grainier, I should say, the more detail, in here versus this one. So. के लिए भी है Photoshop process के लिए भी है क्या? So Photoshop, no, we have not gone to Photoshop at all. This is purely PixInsight currently, right? Photoshop you can still do, but I don't know how you will do LRGB combination with Photoshop. But I'm pretty sure there are plugins that can do LRGB combination in Photoshop. I'm pretty sure Annie's Astro Actions provides that, but I've never really tried it. Here is where I stop, right? This is the point where I say, okay, I have an LRGB master. From this point onwards, I can continue processing it in Photoshop here, or I can push it into, let's say, just as an example, I want to export it and save it as, let's go to data. Let me see if I can push it to, SSD. M45. Let's say I'm going to call this as M45 LRGB, and I'm going to store it. The problem is that once you go to Photoshop, you're going to get only 16-bit from 64-bit because Photoshop doesn't support beyond that. You can't do anything about it. So I'll go here and go to where I stored. I stored it in SSD, AP, M45, this guy. So this is the data that I just created it, and now it's available here. Now you can do a bunch of things. You can do, your friendly Nick plugin, or you can use the Annie's Astro Action. For example, let's try to do something. Let's try to apply some curves, and let's say I'm going to make it a little darker. I'm going to make some little curves transformation, maybe, I don't know, like that. I'm going to do some vibrance control, right, like that. You can do a bunch of these things, and then you'll basically flatten the image. You can do some actions like dynamic enhance, which is brighten it up a little bit more. You can reduce the star size, all sorts of cooking stuff you can do right here. I mean, to me, usually Photoshop, I'm not good at Photoshop. I don't know enough to use it very effectively. I can get by. Basically, I can do masking a little bit here and there. I can do some cleanup and all that stuff, but usually I end up overcooking it in Photoshop. And I know people can do real good things with it, but usually I'll do very minor changes with it, like cleaning up some kind of noise reduction in specific areas, high pass filtering. Those things I can do it in Photoshop, but most of it I complete it in what do you call that, in PixInsight itself. So for example, I want to increase the colors. What I'll do is I'll put a clone like that, right, mask, and then go with curves transformation. There's something called curves transformation. What the curves does is I can look at it and I can first make it high contrast. I can pull this lower bit down, upper bit more, a little bit more contrast. Okay, sure. Then I can do select the saturation and push the saturation up or down. I can desaturate it. I can make it really saturated, however I want, right? I can do selective color saturation using the color saturation tool. I can do unsharp mask in here if I need to, which typically I don't. Some people do, so I can't. So basically, it does provide a bunch of these tools. So I mean, we are pretty much at the end of what I at least wanted to show. Just to show that how you would go about doing an LRGB processing in PixInsight versus some of the other tools that you have. So I said half the battle is acquiring data, but the other half of extracting what you've acquired, that's a different ballgame, and there is no way around it other than practicing it over and over and over again. Either you can download, like one of people download public data, you can process it. I can share my data, you can process it. You want to shoot your data and process, that is the best one, because you know how your data is, and also you will understand why you want to do certain things, like initial calibration, why those are very important. If you'll notice that this original data itself looked good, but I didn't show an important portion, which is called dynamic background extraction. Here is an image. You can see that this is a very typical image that we'll get. You will see that there is a little bit of faint ringing here because my flats failed. You will see that this particular image is brighter on the top, darker on the bottom, mainly because of light pollution, right? I'm getting gradients in it. And you may have complex gradients, right? You may have weird brightness in the corner and bottom corner and all sorts of stuff. So the powerful tool that it provides, and to me, the single most tool that I wanted to use always was dynamic background extraction. This particular tool allows you to model what the background is. You tell the system what the background is, and it will try to generate a model and subtract it out. See, for example, light pollution sources are additive sources, so you need to subtract them out. Flats, like if you have dust and stuff, those are multiplicative, so you need to divide them out. So depending on what you want to get rid of, you want to select the right tool. For example, let's say I want to get rid of this what do you call that, bright source. What I do is I will want to tell that these are my background. I'll basically go and touch areas that has no stars. Basically go as close as you want, and you click on it and say this is my background. And then I need to provide a tolerance. Just as an example, I'm going to give it 1.5 tolerance, and you'll notice that I can even tell it to generate, and it will try to generate as much as it can. But you want to move any sample that fell on a bright structure, and so that it shouldn't try to model that as a background. So let's assume that my objective is to get rid of this gradient, because this gradient is a pain to deal with, pain to process. You cannot really process it well if you have gradients in the system, right? So you will model them out like that. Then I know that this is a light pollution source, which means it's an additive source. So I need to subtract it out. So I'm going to select subtractive correction. And I drag and drop to it, basically. So now it's going to do two things. One, the model, right? And you can see that it detected that here is a darker portion. This area is bright. This area is a little dark. And these parameters that you're seeing, sample radius, sample row, sample weight, smoothening factor, all these can be tuned over and over again. And you can do multiple pass of this thing to get a really, really good model. A lot of times you may want to look at other people's image and say, am I looking at a very faint signal, or am I looking at some light pollution source? And you can subtract it out of it. Very tough when you're dealing with nebula images, right? Because they have a lot of faint images. But in galaxy, it's very simple. Most of the time, you can detect which is your main galaxy, how much of halo is around it, and then everything else is just background, and don't worry about it, right? So you can see that, and here's my subtracted image, and you can see how flat this is, right? Compared to the original one, which is, you can see that there is a explicit gradient right here compared to this guy. And now this guy is ready to be processed. We can really process it well compared to this guy. So dynamic background extraction is probably going to be your first set before you're about to start processing it. So you'll stack it, you'll get your master frame, you will crop out all the edges that has junk in it, like stacking artifacts, Then you probably are going to do this dynamic background extraction. Then you are ready to process it. Okay, so I'm pretty much done basically. So it's any questions, anything that I know that we have went way past our target. We started basically went 2 hours instead of 1 hour, but I thought it would be probably better to reach 9. So Kirti, it's your take control, I guess.
Okay, thanks a lot, Anis. You spent a lot of time with us and then actually shared a lot of information. So this video will also be available for later viewing. I'll try to annotate the time where we discussed all the processes, and leave a comment so that people can just click on those timestamps and see that as well, since it's a long video. So guys, do you have any questions? If not, then we will just stop this session right now, and probably we can have a lot more sessions in the future.
Yep, absolutely. So, I think it will be very helpful for people who have a lot of experience with these tools and planetary. I know a bunch of these guys are pretty good planetary imagers. So it'll be good to exchange ideas and techniques and make it better. And again, we can do some more deep dive sessions on specific functions if you're interested. If I know, I will be happy to show it, as well as planetary. I know some of it I could do, if, whatever I know, but I said I'm not really good at it. We can do narrowband processing at some point as well. It's a little bit more, has more latitude in what we can do. So anywho, that's where we are.
All right, cool. So thanks a lot, everyone, for attending, and special thanks to Anis for doing this. So
Yep, my pleasure. Thank you.
Cool. Have a great day, guys.
Yep. Bye. Talk to you folks later. Bye.